Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon. But it's kind of got to make you laugh to think that you can go all the way to the Moon and back using something that's ultimately just an approximation. Everything in our universe seems perfect. There are laws governing the entire universe, but certain mysteries have remained unsolved despite decades of research. Why does time travel in one direction? What is the nature of reality? Why does gravity exist? Why does time slow down when we travel at the speed of light? These are questions that have fascinated us for millennia. What if I told you that gravity is a lie? It's merely a construct of the human brain. This might seem unbelievable, but that's exactly what the famous physicist Brian Cox recently claimed. Let's delve into the nature of gravity and why time slows down. To find out what on earth is wrong with gravity, we need to go beyond Newton. The problem lies not so much in what he understood, but in what he failed to address altogether. There's a problem with Newton's theory of gravity, and that's that it just allows us to predict how things move under its influence. It doesn't say anything about why gravity exists or even how it works. It just allows you to calculate things. And Newton knew this, of course. He essentially just said that it's down to God. In fact, he said that the most beautiful system of the sun, the planets, and the comets could only proceed under the dominion and counsel of an intelligent being. In other words, I'll give you the tools to calculate how the objects move around, but don't ask me how or why that is. That's down to God. In the vast universe that surrounds us, there are mysteries waiting to be uncovered. Among these mysteries are the perplexing phenomena related to time and gravity, two fundamental aspects of our existence. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity makes a strange twist. Albert Einstein, a name known to many, gave us a new perspective on the universe with his theories of relativity. His work laid the foundation for our understanding of how time behaves under different conditions, particularly when we travel at extreme speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories, the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. In simple terms, it tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One of the most intriguing thought experiments used to explain time dilation is the light clock. Imagine being inside a spaceship moving at an incredible speed, close to the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel in a straight line, bouncing vertically. However, to an outside observer who's not moving with the spaceship, things look different. They see the spaceship moving at high speed and observe the light beam's path forming a zigzag. Since the spaceship is moving, the light beam has to cover more distance to hit the mirror. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a diagonal path. Now, here's where it gets interesting. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. But since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. So, in this scenario, time behaves differently depending on your motion. It's not just a concept. Experiments have confirmed these relativistic effects. For example, particles and particle accelerators, like the Large Hadron Collider, can reach speeds close to the speed of light. Scientists must consider the effects of time dilation to make accurate predictions and measurements. The special theory of relativity opens the door to a world where time is not a constant, where it can be stretched and compressed depending on your motion. It challenges our everyday intuition and leads us to the realization that the universe operates in ways far beyond our common experience. Einstein's special theory of relativity, introduced in 1905, was followed by his general theory of relativity, which further advanced our understanding of gravity. The general theory of relativity describes gravity not as a force acting at a distance, as Newtonian mechanics did, but as the curvature of spacetime caused by mass and energy. This concept not only explained gravitational phenomena like the orbits of planets and the bending of light, but also predicted exotic phenomena such as black holes and gravitational waves. One of the more mind-bending aspects of general relativity is the concept of gravitational time dilation near massive objects. Just as time slows down when we move at high speeds, it also slows down in strong gravitational fields. This means that time passes more slowly for an observer close to a massive object compared to someone farther away. This effect has been observed and measured. For example, precise atomic clocks placed at different altitudes show that time runs slightly faster at higher elevations, where the gravitational pull is weaker. The implications of general relativity are not limited to extreme cosmic phenomena. They also play a crucial role in understanding the large-scale structure of the universe. The expansion of the universe, first observed by Edwin Hubble, is explained by the general theory of relativity. The theory describes how the fabric of spacetime itself can stretch and expand, carrying galaxies with it. General relativity has transformed our understanding of gravity and the cosmos. It reveals that gravity is not a mysterious force acting at a distance, but a consequence of the curvature of spacetime caused by massive objects. This elegant idea has been confirmed by numerous observations and experiments, from the bending of starlight to the detection of gravitational waves. Einstein's theories challenge us to think deeply about the fundamental nature of spacetime, time, and the universe itself. They suggest that our intuitive understanding of reality may be limited, and that the cosmos operates in ways that defy our everyday experience. Theories like relativity remind us that scientific knowledge is a journey of discovery, where each breakthrough leads to new questions and deeper understanding. In conclusion, Newton's theory of gravity laid the foundation for understanding the mechanics of celestial motion, but it was Einstein's theories of relativity that revolutionized our understanding of gravity as a fundamental property of spacetime. The special theory of relativity introduced the concepts of time dilation and the constancy of the speed of light, challenging our notions of time and simultaneity. The general theory of relativity further advanced our understanding by describing gravity as the curvature of spacetime caused by mass and energy. Einstein's theories continue to inspire and guide scientists in their quest to understand the universe at both the largest and smallest scales. They have reshaped our view of the cosmos, revealing a universe where space and time are intertwined, and where the force of gravity is a manifestation of the geometry of spacetime itself. As we continue to explore and experiment, Einstein's theories remind us that the universe is full of mysteries waiting to be uncovered. Each new discovery brings us closer to unraveling the secrets of the cosmos and understanding our place within it. Albert Einstein's theories of relativity, particularly the special and general theories, have had a profound impact across physics and astronomy, reshaping our understanding of fundamental concepts such as spacetime and gravity. The special theory of relativity revolutionized how we perceive space and time by introducing the idea that the speed of light is constant for all observers, regardless of their motion relative to the source of light. This constancy implies that time and space are not absolute, but are intertwined in what Einstein termed spacetime. The theory also predicted phenomena such as time dilation and length contraction. Time dilation means that time passes differently for observers in relative motion. Moving clocks run slower compared to stationary ones. Length contraction suggests that objects moving at high velocities appear shorter in the direction of their motion when observed from a stationary frame. These predictions have been validated by numerous experiments involving particle accelerators and cosmic ray collisions, confirming Einstein's theoretical framework. Einstein's general theory of relativity expanded on these ideas by presenting gravity not as a force acting at a distance, as described by Newtonian mechanics, but as the curvature of spacetime caused by the presence of mass and energy. According to general relativity, massive objects like stars and planets warp the fabric of spacetime around them, similar to placing a heavy ball on a stretched rubber sheet. This curvature affects the paths of objects moving through spacetime, including the trajectory of light. The theory gained substantial experimental support during a solar eclipse in 1919, when observations of starlight bending around the Sun confirmed Einstein's predictions, providing strong evidence for the theory. General relativity also predicts the existence of black holes, regions where the gravitational pull is so intense that nothing, not even light, can escape. These predictions have been substantiated by observations of stars orbiting invisible companions, likely black holes, and by the detection of gravitational waves from merging black holes using instruments like the LIGO and Virgo detectors. Gravitational waves themselves are a direct consequence of general relativity, representing ripples in the fabric of spacetime caused by accelerating massive objects. Their first direct detection in 2015 marked a significant milestone in astrophysics, confirming Einstein's theory and opening a new era of gravitational wave astronomy. These waves provide a unique way to study violent events in the universe, such as the collisions of black holes and neutron stars. The theories of relativity have not only expanded our understanding of the universe, but have also led to practical applications in technology. For instance, the Global Positioning System, GPS, relies on precise timing measurements from satellites in orbit. Due to their high velocities and the weaker gravitational field at their altitudes, the clocks on these satellites experience both special and general relativistic effects. Engineers must account for these effects to ensure the accuracy of GPS navigation. Beyond technological applications, relativity has deepened our understanding of the cosmos. It has provided insights into the large-scale structure of the universe, the behavior of objects in extreme gravitational fields, and the fundamental nature of space and time. Einstein's work has inspired countless scientists and continues to be a cornerstone of modern physics and cosmology. While relativity has answered many questions, it has also raised new ones. One of the most significant challenges in physics is unifying general relativity with quantum mechanics, the theory that governs the behavior of particles at the smallest scales. Efforts to develop a theory of quantum gravity, such as string theory and loop quantum gravity, aim to reconcile these two pillars of modern physics, but a complete and consistent theory remains elusive. In conclusion, Einstein's theories of relativity have transformed our understanding of spacetime and gravity, providing a framework that describes the behavior of objects from subatomic particles to galaxies. Their predictions have been confirmed by numerous experiments and observations, leading to technological advancements and deepening our comprehension of the universe. The quest to understand the interplay between relativity and quantum mechanics continues, promising further discoveries and insights into the fundamental nature of reality.